This video will cover chapter 4 of the OCR chemistry specification. We'll cover all the points presented here. So, the first main definition that you must know for this chapter is acids. Now, acids are any compounds that have hydrogen atoms that can dissociate, and in water, acids release hydrogen as protons into solution. Now, the highlighted part being the main point, that acids release hydrogens as protons when in aqueous solution. Now, you'll be able to get the marks for this definition by simply saying acids are any compound that dissociate in aqueous solution or dissociate protons in aqueous solutions. Now, here is an example of an acid equation. HCl, which is an acid, plus any aqueous solution produces H plus and Cl minus. Now it's an acid because this H plus proton is removed. Now some common acids that you need to know are HCl, H2SO4, and HNO3. Strong acids, examples being HCl, release all of their hydrogen atoms into solution. So therefore, if you were ever asked in a question to define a strong acid, the definition would be any compound that completely dissociates in aqueous solution. With an example being, as shown above, HCl aqueous goes to H plus Cl minus, both still being aqueous. Then there are also weak acids. Weak acids, such as CH3COOH, only release a small amount of available hydrogen atoms into a solution. Therefore, if you were asked for the definition of a weak acid, it would be any compound that partially dissociates in aqueous solution. Now, these two definitions are very key to this chapter and must be of note. A good example for weak acids is the one mentioned above, CH3COOH aqueous goes to CH3COO minus plus H plus, both being aqueous. Now you can see there are some hydrogens that are still available within the compound, as opposed to HCl, where there are no hydrogens in that chloride ion anymore. Now, there are more definitions that you must be aware of. One of them being a base. A base is any compound that neutralizes an acid to form salt and water. A salt is a compound formed when H plus ions of an acid is replaced with metal or any positive ion. An alkali is a base that dissolves in water, releasing OH minus ions. An example is sodium hydroxide, NaOH, as a solid, plus any aqueous solution, forming Na plus OH minus. So as you can see, as opposed to an acid, which would have H plus, sodium hydroxide releases OH minus, which makes it an alkali. An example of a base that's not an alkali is copper hydroxide, zinc hydroxide, and silver hydroxide. Now, common bases that you must be aware of are as follows: metal oxides, metal carbonates, and alkalis. Now, another point to mention is that the definition of a salt can be fairly confusing. A compound formed when a H plus of an acid is replaced with metal or a positive ion, right? That's a very complicated definition to remember. But a good way of remembering it is just by thinking of actual table salt. Now, actual table salt is, of course, NaCl. Now, you can see that NaCl is comprised of two things. It's comprised of Na plus and Cl minus. Now, Cl minus can be HCl. Therefore, that means that HCl, which is an acid, as said in the definition, has its H plus ion replaced with sodium, which is a metal. Now, that's a very easy way of remembering what that definition could be. If you just work back from table salt, you know that it is when the H plus of HCl is replaced with Na, a metal, to form NaCl or table salt. Now, another fairly large definition in this chapter is a neutralization reaction. A neutralization reaction is when H plus ions react with a base to form a salt and neutral water. Now, that alone is the definition that you must write when asked in an exam question. This includes acids reaction with metal carbonates and alkalis as well, as they're both considered bases. You can see here metal carbonates and alkalis are both considered bases, so therefore acids reactions with these two would also be considered a neutralization reaction. It's not just a reaction where a base such as NaOH reacts with acid to form water and H plus and salt, but it can be metal carbonates and metal oxides as well for that matter. So, an example of how you identify and write out a neutralization reaction. So, we're given this equation, HCl plus NaOH. Now this we can tell is a neutralization reaction because HCl is an acid and NaOH is a base. So we know that it will form H2O and some salt. Step number 1 would be to identify the H plus and the OH minus, where these come from. We can see that the H plus will always come from the acid because acid is a proton donor. It gives off H plus ions when in an aqueous solution. So this is the H plus and that's where it will come from. OH minus we know comes from a base because it dissociates to form the positive ion and the OH minus. So this will come from here. And you join these two together to form the water. This is where the water comes from. So we can write plus H2O because there's one H here, another H here, and oxygen. So these will join to form H2O. Step number 2 is simply to just join the remaining elements together. The remaining elements would be sodium and Cl to form sodium chloride. And that's as simple as writing neutralization equations go. Now these steps are usually only for alkalis because alkalis contain a form of hydroxide ions, OH minus. So that's why it can be done fairly easily. However, with metal oxides and metal hydroxides, there is a different rule. That's because there's usually only a supply of O minus from the metal oxides and metal hydroxides, as said in that comment below. So therefore, to do this, we can simply write out plus H2O, because we know H2O will always be given off, and then work backwards from here to be able to understand what the remaining element would be. Well, H2O, we can see that there's 2 hydrogens in the acid, and we can see there's an O minus from the metal oxide. Therefore, these two we know will join together to form the water. Now we can just join Cu and SO4. CuSO4. We know that SO4 is a 2 minus ion, Cu is a 2 plus ion, so therefore they can just react to form CuSO4 with no numbers in between. Now, looking at these reactions in terms of OH minus and H plus, we can see that the ionic equation for a neutralization reaction will always be H plus OH minus goes to H2O. This will always be the ionic equation for a neutralization reaction. To show that this will always be the ionic equation, we can just really quickly work out what the ionic equation is of this neutralization reaction as shown. So we split up all of the elements into their ions, H plus Cl minus, Na plus OH minus goes to Na plus Cl minus. And remember, H2O is always a liquid, so we forget that and we completely leave it out. And then just crossing off things that appear on both sides, Na plus, Cl minus. This drops down as just regular H2O, it's a liquid. and we get H plus OH minus goes to H2O. This will always be the ionic equation. Now, acids can also be neutralized with carbonates. Carbonates are any compounds with CO3 2 minus ions. So examples of this being ZnCl3, MgCl3, and more. So the general equation for an acid with a metal carbonate is always going to follow this format. An acid plus a metal carbonate produces a salt, water, and carbon dioxide. So even if we rub this out and try it to attempt it ourselves, using the steps that we were able to bring in from the previous examples, we know just to write out what we already know will come about, which will be plus water, H2O as a liquid, plus CO2 as a gas. So from this rule, we already know that water and carbon dioxide will be given off regardless. Now, just looking at the two reactants, we can see that carbon dioxide will have one carbon coming from here. It can have, for instance, two carbons coming from here, so two oxygens coming from here. So there's one oxygen there, and that's about it. And then for water, we know that now this is a metal oxide. This will have an O minus. This O minus we can use for the water molecule, and these two hydrogens we can use for the water molecule. So we just add these two elements together, and that is ZnSO4. And that's it. Now, the second part of this chapter is all about acid-base titrations. Titration is a technique used to accurately measure the volume of a solution that reacts exactly with another solution. Now, what is titration used for? Titration is used to find the concentration of an unknown solution, identify unknown solutions, or finding the purity of a solution. Now, a standard solution, which we covered in a previous video as well, has the general definition, solution of known concentration and volume. Now, we will be going over the steps to titration. The best way to learn this is obviously by doing a titration yourself, which is part of this spec anyways. The first step is usually to prepare a standard solution. Now, this is not part of the titration itself, and it's technically a separate experiment, but just for the sake of putting both experiments in one, we're going to lay it out now. First step is that the solid is weighed. Second step is the solid is dissolved in a beaker using distilled water. Third step is that the solution now is transferred to a volumetric flask, and the traces of solution are washed into the flask, of course, with distilled water. Lastly, then the flask is filled to graduation line by adding distilled water. Now, this step is very important, and if the graduation line is passed, the whole standard solution must be done again. Reason being, in terms of moles is equal to concentration times the volume. If this volume increases too much, the concentration is going to have to decrease. So if you add too much distilled water, the concentration of that solution will therefore decrease. That means that you can't just take out the water and adjust it so that it is at the graduation line, because the concentration will have changed, and therefore the whole experiment must be done again. Lastly, the flask is inverted several times. This is, of course, just to mix the solution. Now, for the titration itself, step number 1 is to add a measured volume of one solution to a conical flask. Now, this is usually the standard solution. The reason being is because the standard solution is a solution that you know the concentration and the volume of, meaning that we can use those values within this solution to figure out the identity or the purity or whatever else that we need to identify through the titration. So this is a little example. This volume is the solution of known concentration and of course volume, but there's no need to add that. Now, secondly, we add the other solution, which is usually the unknown solution, however it doesn't necessarily have to be, to a burette and record initial burette to the nearest 0.05 centimeters cubed. Now you can see that here, this is the unknown. Now, we need to add an indicator to the known sample. So that would be in this conical flask here. We'd add an indicator, usually phenolphthalein, and that would turn it purple. Now, we drop the solution into the conical flask until solution in the flask changes color. Now, this would obviously be the starting burette, and then the final burette would be somewhere around here, let's say, endpoint, and then this is the original sample, and we slowly drop, 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 until it changes color and turns usually clear. The thing to note is that a quick trial is usually done for an approximate titer. This means that when we run this initially, we can just very quickly run a bunch of droplets into the conical flask just to get a rough idea as to where the titer would normally be, and therefore it makes the whole process of getting the readings much more simple. Another note is that the titration is repeated until two concordant titers have been found. Now, concordant titers are any titers within 0.1 centimeters cubed. Now, this means that a titer such as 22.5 centimeters cubed and 22.7 centimeters cubed, we cannot just stop there. We must get at least two concordant titers, so something like 22.5 and 22.4 centimeters cubed will be found. Now, the best way to understand how to answer these questions, especially for chapter 4, for all the chapters, but especially for chapter 4, is just to do exam questions. So just really quickly, I want to run through an old exam paper that covered all of chapter 4 up until what we've done so far. So what is meant by an acid? Well, an acid, we've already said, is any compounds that release hydrogen ions in solution or water. Now, alternatively, although this is the definition that I've given you within this chapter, we know from A2 that for the questions such as these, you will also get the marks by simply saying a proton donor. That is all you need to say for this mark. Now, this is also the definition. You also get marks for saying this. However, this is far simpler and we learn it in A2. But you will still get the marks if you say it in an AS paper. Now, what is meant by a weak acid? A weak acid, we already know, is any compound that partially dissociates H plus ions in solution. Now, here goes a very good titration question. If you can answer this question front to back without any help, I believe you know titration fairly well and are ready for the exams. A student carries out a titration to determine the mass of citric acid in a lime. The student follows the method below. Squeeze the juice out of 2 limes. Transfer the juice into a 250 centimeters cubed volumetric flask. Now, I always recommend being able to visualize the questions, especially if it's a practical question such as this. But if you can't do that, then it's a very good idea to just draw out what's happening within the question. So the juice is transferred to a 250 centimeters cubed volumetric flask. So this is that juice. And made up to the mark using distilled water. Oh, so then we can identify from what we just went through that this is the standard solution, which is the solution that we'd have the known concentration of. Now, the student then pipettes 25 centimeters cubed of the diluted lime juice into a conical flask and added a few drops of phenolphthalein indicator. So this means that now into a separate conical flask, the student has added 25 centimeters cubed and added phenolphthalein indicator. So this is that standard solution that we were just talking about. He then titrates this solution with 0.8 moles per decimeter cubed of sodium hydroxide. So that means that within this titer here, oh, I guess they've given us it right here. This is 0.8 moles per decimeter cubed NaOH. The student carries out a trial titer followed by 3 further titrations. The diagram below shows the burette readings for the 3 further titrations. Each reading is measured to the nearest 0.5 centimeters cubed. Okay, well, let's get on to the questions. Question number 1. Record the student's burette readings in the table below. Calculate the mean titer to the nearest 0.05 centimeters cubed that the student should use to analyze the results. Well, let's go to titration number 1. Titration number 1, we can see, is about 27.12335, I'd say. 27.35. Now, of course, within questions such as these, they will give you a range to be accurate. 27.35, and we know that the initial reading was 0.00. Now, big note. In titration questions, always to at least one decimal place. Now you can see the 0.00 is the exact same as if we just wrote 0. We cannot get the marks just for this. We need to make sure that everything in all the columns are to the same number of decimal places. We know from the question that it's to the nearest 0.05. Therefore, we know that for this question, they want it to 2 decimal places. But at the minimum, it must be to 1 decimal place. So, reading off the second titer, we can see that the initial reading was 0.10, and the final reading was 27.1, 2, 3, 4, 5, 6, 27.65. Remember, we're reading from the meniscus. Now, just doing the calculations really quickly, we can see that that is 27.35. Sorry, I said this was initial reading was 0.05, right? Because of the meniscus. I might have gotten that wrong, but I know that it's 0.05. Just being able to distinguish that it's within 0.05. That wasn't good, but I'm sure you guys spotted that mistake as well. This is 27.55, and this is 27.40. Now, When calculating the mean titer, you only ever include the concordant titers. Now we can tell that these are the two concordant titers because they are within 0.1 centimeters cubed of each other. So we'll use these 27.30 plus 27.40 all over 2 gives us 27.35. Now, this next question is the really difficult question, but we'll go through it together. Citric acid is neutralized by NaOH, right? As shown in the equation below. Calculate the mass in grams of citric acid in 1 lime. Now, 1 is in bold, so I know that this will be very important for me to come back to. Assume that citric acid has a molar mass of that and is the only acid in the lime juice. So, going back to the question, I'm just going to quickly write down a couple things. So going back to the question, I'm going to write out the 2 compounds that I'm concerned with. And that is the C6H8O7 and the NaOH. Now, using this information, I know that I've got 0.8 moles per decimeter cubed of NaOH. So concentration is 0.8 moles per decimeter cubed. And I have that within my titer. So therefore, I know that my volume is this volume that I just calculated as 27.35. So I can just quickly convert that in my head to decimeters cubed. So that's 0.02735 decimeters cubed. And then for C6H8O7, I know that I have I have 25 centimeters cubed in the conical flask that I've pipetted out from 250, and that I've squeezed out of 2 limes. 2 limes. So that's where I have to go back to when I'm calculating my final equation. So I know that the volume here is 0.025 decimeters cubed, but I know nothing else, and I need to work out the mass. So I know that this is a 3-to-1 molar ratio. So this means automatically I've got concentration volume. I can calculate moles of NaOH. Moles is equal to concentration times the volume. I know that the moles of NaOH will be 0.022 moles. Using that 3-to-1 ratio that I noticed before, I know that I have to do this divided by 3 to give me 0.0073 moles. 0.0073 moles of C6H8O7 in 25 centimeters cubed. Now, I'm concerned about 250 centimeters cubed. The reason why I'm concerned about 250 is because I had 250 in my original volumetric flask. So I have to make up, I have to count up, I have to account for that ratio. This is being multiplied by 10. Therefore, I can just multiply this by 10 because what you do to one side, you do to the other. So that's 0.073 moles of C6H8O7 in 250 centimeters cubed. Now, what I need to do is I also need to account for the fact that I want this in 1 lime. This is the information for 2 limes. So this is in 2 limes. I want this in 1 lime. To go from 2 to 1, I just divide by 2. So I just have to divide all of this by 2. This gives me 0.0367 moles in 1 lime. Now, I know the moles and I know the molar mass. I can very easily just do moles equal to mass over molar mass, which means that moles times molar mass is equal to mass. which means moles times molar mass is equal to mass. That means 0.0367 times by 192, which I got from the equation, is the mass in 1 lime, which is 7.04 grams. Now, here are the steps to that question that we just did. My recommendation would be for you to write out these steps and retry that question that we just went through together, but by your own accord, pausing the video and then starting the video back up again to see if you got it right or got it wrong.